Now this is a set then of the alternating. What's the alternating set? It's the set of all elements that are even permutations. And this is the total symmetric group. We'll think of it as the set of all permutations, even and odd, and each permutation is one or the other. Okay, and it was just the same again. So this whole thing here, what is that? Well, it'll be my B. Okay, it'll be my B. So this thing here on the right hand side is the set of what? Odd permutations, right? Okay, so I can sort of call that. I can call that like B of n. Actually, I just call it B. I'm not quite sure what size it is. See, we're trying to prove that the size of these two is equal. So I better not put an n here. So this here, whatever size it is, see, we're trying to show that that you can map. Now, if you can map this set to this one bijectively, so 1 to 1, then that's the heart of the proof, right? Then you've got it. If now since these two here, or for B, it's just this S minus A is just the set of odd permutations, right? Because this is the total set of all permutations minus, throw out all the permutations that are even, and what's left is the set of odd permutations, because there are only two kinds. Okay. All right. So if we can prove a bijection between this and this, we've effectively proved a bijection between these two sets. Okay. Now, if that's the case, if it's 1 to 1 between these two, then the size of this must be the size of that, and that's sort of the motivation behind the proof. That's why you do it in this form. All right. Okay. So that's the function between the left-hand set and the right-hand set. Now that's between sets, but what about elements? How do you actually go about that? And that's also provided in so let x just be a member of a to the n, and this is just given in the question. You're given this, and you're asked to prove that f is a bijection. Now, what on earth is going on here? Now, it's rather ingenious, proof. Now, x is just an arbitrary member of your alternating group, but we're talking about in the context of sets now, because we're not interested in the f of mn. We're not trying to prove isomorphism. We're just trying to prove these two are the same size, right? So just bijection's enough. We just need to prove that this f here is bijective. In other words, it is injective and surjective. Okay. We're just trying to show the size of these two are the same. All right. So what is this? Now, on the left-hand side, we're mapping from this set to this set. Okay. Now, x here is just an arbitrary member of the alternating set, right? And what are we doing here? Well, now we're talking in the general context of permutations, right? So this x here will be an even permutation, okay? And then we're applying a what is this? 1 to 2. What is that? That is a what's the word? I'm trying to remember the word. Transposition. Transpose. Right? Put across put. This is a transposition. Now, can you remember the theorem on the previous sessions, because we're going to need it here, and that's the motivation. We're now talking about the well-formedness of F. We're discussing that now. Is this well-formed? What does it mean, and what's the point? Well, now X, well, the theorem. The theorem says that the order of any permutation, whether a permutation is odd or even, will depend on the number of transpositions it has. So now a transposition, can you remember, is an odd permutation. That was one of the theorems. Go back a little bit. So a transposition is an odd number, is an odd permutation. Transposition is an odd permutation. All right. And X here is a member of the alternating set, and that means it's even. That means that this member has an even number of transputation. Trying to remember the term. Can't remember the term. All right. Anyway, so this will. Look, I should look it up. What's the I'm forgetting the term. It's a cyclic group of order 2. What is the word? Transposition. The position. Transposition. Okay. So this even permutation will have an even number of transpositions. Okay. And here's one more. See, it's just a cycle. Its length is 2, therefore, by definition, it's a transposition. And so you've got one more. So the whole thing, you'll have an even number of transpositions plus one more. So that'll make this whole thing have an odd number of transpositions. And therefore, now B, the right-hand side then, B is, that's the set of odd permutations. B is the set of odd permutations. And that means each member of B has an odd number of transpositions. Makes sense? Okay? So this is well formed. Okay? Your X has an even number of transpositions because X belongs to that. A then, that's the even set of even permutations. And this is the set of that'll have an odd. This member here will have an odd number of transpositions. Okay, so it makes sense. So you're mapping a permutation which has an even number of transpositions, in other words, an even permutation, into an element that has an odd number of transpositions, and therefore belongs to this set B, which is the set of all the odd permutations. So this makes sense, right? So it's well formed. Quite a bit of discussion there, and quite ingenious, right? Okay, now we have to prove the bijectivity. We've discussed the well-formedness. This is a well-formed suggestion, proposition. And remember, when you're trying to prove a mapping, the choice of the mapping, especially at member level, so this is like set levels, this is member level, that choice is critical because the rest of the proof depends on it. And this is rather an ingenious one. Okay, so now to prove injectivity, to prove that f, this function, this mapping, is injective, remember that you just choose arbitrarily two members of your we'll call it B, right? So we're trying to prove injective, right? So this is your domain, and this is your codomain, and so let A and B belong to your domain, and so they will map under F into the codomain. And remember, to prove injectivity, you just take two members of your codomain and you let them be equal. Okay, so something like this. And then you aim to show, so if injective, then if these two are equal, then these 2 points have to be the same. So that implies A equals B. Okay? Now we've done that many times, so I won't labour that at all. All right. So A and B, A and B belong to A then. Right? So your A here is your domain, your starting set. Okay, so what is F of A? Well, it'll be 1, 2, A, right? And you just here, you just A here, so A here. So this will be 1, 2, B, right? And we've got to try and prove that A is B. Well, how can we get rid of this transposition that's on the left on both sides? Well, just apply another permutation that's just the same. So we'll just do it twice. So 1, 2, 1, 2, A will be 1, 2, 1, 2, B. Now why did I do that? Well, if you apply transposition twice, what do you get? I mean, think about what a transposition is, right? I mean, in general, a general transposition is of this form. I don't know, let's call it P and Q. Right? Let's say it's P goes to Q and Q goes to P. Right? So effectively, it's just a swapper, right? P and Q swap. These two objects, object P and object Q, they just swap positions. That's what a transposition does. Now, if you swap it twice, once and then twice, you just end up the way you started with. You end up with what you started with. Okay? So if you do PQ twice, it's just E, right? They cancel each other out.